on similar topics, and it's partly because of the success of that that we welcome the opportunity to look at this area again as part of our programme, and it's obviously a popular topic, and we're delighted to see so many of you here today. Can I just, by way of a courtesy, thank the FACS group for providing such a distinguished group of speakers for us, and I'm sure we're in for a fascinating afternoon. A couple of words of explanation about the format. The afternoon will be in 2 sessions, and again our thanks to the FACS group for providing tea and coffee in the interval. If you feel really grateful, their membership secretary will be standing at the back with forms should you wish to join. And I hope some of you who are keen will indeed do so. Membership of the Conservation Society is free. We are circulating sheets. There are sheets, I think, at the front which will work their way back. We invite you to sign those. If you do want to join, we'll be happy to add you to our list. And we will also make those lists available to the Formal Aspects group as well, so they have a record of everybody who attended today. Just a possible moment of excitement. There is painting work going on in the main part of the museum. We have been warned that there is a small probability, it's not stated, a small probability, possibility, that it might set off their fire alarm. If it does, we will be escorted from the building. So should it go off, it is almost certainly caused by fumes from the paintwork rather than anything more serious, but we will need to leave the building. So don't fear perhaps quite as badly as you might otherwise if it does go off, but we hope very much it won't. I think on that happy note, it gives me great pleasure to introduce Professor Cliff Jones. Well, I say introduce again. Cliff has been part of the British computer science community for many, many years, and it's a great pleasure to have him here today. And Cliff is going to act as the session chairman for the first part of today. Cliff, contrary to rumours I've been spreading, is still very fully engaged in his studies at the University of Newcastle upon Tyne. I did say to somebody, I thought he'd recently retired. I am so sorry for having said this. And it is completely untrue. And Cliff will now demonstrate to us that he is as busy as ever. Cliff, can I give you the microphone? And,
I was going to pass that over to John. Okay, well, thank you very much, Roger. Can I add my words of welcome? It's absolutely super to see old friends and some new people I've never met before. I really think that's the purpose of this event, to bring along some speakers who some of the younger people may have only heard about and hear their version of the story. So I think we're in for a good afternoon. Roger has mentioned in 2001, I had an approach from my old friend Chris Burton to come and give a talk on the history of computing. I'd written a paper which has since been published in the Annals of Computer History, and my reply was, I think I can do rather better than that. And we set up an event which was definitely better. We had Tony Hoare, Joe Stoy, Robin Milner, and somewhat tentatively a gentleman sitting in the audience, Peter Landin, who I was so nervous, Peter, that you wouldn't actually speak, that I had a talk in my briefcase in case you chose not to. I'm not sure I've ever told you that. To my and everybody else's enormous pleasure, and as a total surprise, John Reynolds and his wife Mary walked into the room that day unannounced. I had not expected them to be at the event. And that was tremendous and extremely kind of them. And we said, one time when John is over in the UK or over in Europe, we will do another one of these events focused around John's attendance. And I'm sure Gordon doesn't mind me saying that. So this event is timed to fit with John Reynolds' schedule. John will speak first, Gordon will speak second. In the previous event, I didn't get to give a talk. I've been less modest this time, and I have scheduled my talk at the end of the session. All of the speakers are going to try and finish in enough time to leave you an opportunity to ask questions and have a discussion. So without more ado, if I can hand over to John.
Cliff, I'm delighted, particularly to learn that you are continuing your studies at Newcastle. I hope that your degree will soon be forthcoming. I don't intend to speak except tangentially about my own work today. Instead, I want to give a talk based on a paper I wrote back in 1993 at the invitation of Olivier Danvey on the history of the discoveries of continuations, which is fundamentally an interesting topic because it's an extremum in the number of independent discoveries of a significant scientific concept that occurred independently. And the obvious question is why? Part of it, of course, is just bad communication. You'll notice that a number of the field was very new back in the 70s. A number of the discoverers are graduate students working on their theses in widely separated places. On the other hand, the discoveries were also in a wide variety of different contexts. And I think that's a contributing factor. Another point to make is that if you actually sit down and ask who discovered continuations, you eventually come to the conclusion that that is not anything but a vague question. The actual situation is more like people start to explore an archaeological site. Somebody finds a little piece of stone over here, and he brushes it off and uncovers it a bit, and someone else does this over here, and someone does more over here, and eventually it becomes apparent that they are all uncovering bits of the same big thing. And eventually, much later, enough of it is uncovered that we can really tell you what the thing is and describe its shape. And the question of who exactly are the people who made this discovery is, fortunately in this case, not of concern to patent lawyers. I think Olivier invited me because I was active in the area at the time. I knew many of the participants. I knew enough about the subject to understand most of what was going on, and I have no claim whatsoever to having discovered continuations. And I am not at all a scientific historian. I have a great innocence in that field, which raised difficulties at points. Is that readable from the back? No, okay. Maybe I can move this back a little further. I think the story of continuations begins with Algol 60, simply because it was the first language which was sufficiently rich that continuations became a useful tool for understanding the language. One wouldn't speak about continuations with respect to Fortran simply because they would not contribute particularly to your understanding of it. But They were a concept which one had to at least have sensible suspicions about in order to either implement that language or describe it carefully. For example, if you look at the early writers of Algol compilers, they noticed first of all, and Peter Naur's, well, the quote is from Peter Naur. I'm not trying to attribute some things to Naur, others to Dijkstra. That when you treat a label in Algol, as in many more recent languages, as a kind of data or as a value, you have to actually make that value what he calls a program point, which is a pair of entities. One is the code to, or a pointer to the code, which one would expect in any case, and the other is a dynamic pointer to some part of the environment showing where the data that code is to be run on is. It's actually a particularly simple case of what Landin calls a closure. And then they made the realization, as Dijkstra mentions here, that what he calls the link, and many people would call a return address, is exactly the same as a parameter that passes a label value. That is, it too is a program point. And once you treat it as a program point, it becomes a parameter in exactly the same sense that the other parameters of the procedure are. And then, of course, the act of calling the procedure is nothing but jumping to the program point at the entry of the procedure while modifying the environment in that program point to include the parameters. And program points are, in fact, a representation, if you like, of continuations. And then, very soon thereafter, if not simultaneously, Peter Landin started to describe Algol in terms of a call by name lambda calculus enriched with assignment. And he defined that lambda calculus by means of an automaton that he called the SEBD machine. That was an acronym for the four components of the state, which were a stack, an environment, a control, and a dump. And the dump, in fact, encoded the remaining computation to be executed after the control was exhausted. So in retrospect, it was representation of the current continuation. Landin later extended the system by introducing a control operator J that basically allowed you to embed data as values, and therefore gave the language the same power that you get with catch and throw, for example, in Scheme. I think that illustrates a little bit why it's hard to say exactly what constitutes the discovery of continuations. When I originally wrote this paper, I spoke of the program points and the dumps as precursors of continuations because they were not functions. And I think now that was just a very narrow viewpoint of the matter. Shortly, now a couple years later, there was a talk by Wijngarden in Vienna at a meeting with the marvelous name Formal Language Description Languages, in which he showed how to take an Algol program and to translate it into a subset of Algol, in which specifically the go-to operations were eliminated.
John, can I make an observation?
Mm-hmm.
Although the proceedings came out in '66, the date of the conference is '64.
Oh dear, I'm sorry. Okay, I tried to be careful. I hope I was more careful about dates like that in the paper than I was when I made this slide. So it is, I'm sorry. everyone knows this. Some of these dates are when they got the idea. Some of these dates are when they gave the talk. Some of these dates are the first circulated manuscript. Some of these dates are the date of publication. And some of them are just plain wrong. What he, in retrospect, we can see is that he described what's called the continuation passing transform. And it's worth reading the way in which he described it, which is uniquely syntactic. Provide each procedure declaration with an extra formal parameter, specified label, and insert at the end of its body a go-to statement leading to that formal parameter. Correspondingly, label the statement following the procedure statement, if not labeled already, and provide that label as the corresponding actual parameter. Which makes the procedure return explicit in the sense that Dijkstra was speaking of, but now he's talking about pre-processing of the language, if you like. Then what he does is what I call avoiding pass-throughs. When you jump to a label, I'm sorry, if you have a labeled statement in a program in a normal language, you can reach that statement either by jumping to the label or passing through from the previous statement. And here, he inserts extra go-tos so to eliminate all the pass-throughs. The only way you get to a label statement is by jumping. And now he sticks a go-to statement going to the first statement of a block at the end of each block, and presto, you write before each label the word procedure. You replace the colon following it by a semicolon, and use. Isn't that marvelous? Describe each go-to. That's. I'll come back to that in just a minute. Back in those days with proceedings, they recorded the discussion and laboriously reproduced it after the papers, which doubled the price of the proceedings and stultified the discussions. But there are some real nuggets in it. This shows clearly that Wijngarden understood the continuation passing transform. McIlroy basically said, gee, this actually changes the temporal existence of values. How can it preserve the meaning? And Wijngarden, you can almost hear him saying this. I suppose you have a certain implementation of the procedure call, and I suppose you have a certain implementation of the procedure call in mind when you say that. But this implementation is only so difficult because you have to take care of the go-to statement. However, if you do this trick I devised, then you will find that the actual execution of the program is equivalent to a set of statements. No procedure ever returns because it always calls another before it ends. And all of the ends, all of the procedures will be at the end of the program. 1 million or 2 million ends. If one procedure gets to the end, that's the end of all, and therefore you can stop. That means you can make the procedure implementation so it doesn't bother to enable the procedure to return. That is the whole difficulty with procedure implementation. That's why this is so simple. It's exactly the same as a go-to, only called in other words. Well, therein lies a mystery. That is a completely clear explanation of the CBS transform. And it was like it never happened. And this was a meeting where everyone was there. Everyone who was seriously involved in the field at that time. In the discussion of this paper, there were mentions by Dijkstra, by Hoare, by McCarthy, McIlroy, and Strachey. And also present at the meeting were Böhm and Algol and Landin and Neva. And yet, for example, Strachey wrote a paper on continuations perhaps 8 years later, 7 years later, in which there is no mention of this paper. I asked Wadsworth if he had read the paper, and he said, I must have. he said it was in the most important book on the subject, and it was sitting on the table outside the office, and there wasn't that much to read. He said, I never connected it with continuations. So, my suspicion, which was completely incorrect apparently, was that Van Wijngarden, because of his rather extreme attitudes about the syntactic nature of defining programming languages, wasn't taken seriously. But I had the good sense of caution that I took a preliminary version of this history and circulated it to everybody I thought might be able to contribute something. And the replies I got made it completely clear that I was completely off base on this. The most reasonable, or I wouldn't say the most reasonable, but the most intelligible and detailed one was from McIlroy. Van Wijngarden's argument shone clearly and unforgettably, but an idea can be understood without all its ramifications being seen, even by its originator. Since Van Wijngarden offered no practical examples of continuation passing, nor any theoretical application, save as a trick for proving one isolated and already known result, the value of continuations per se came through. And I would say now in more bald terms that while he clearly explained the continuation passing transform, he did not isolate and define the concept of a continuation. For him, they were just procedures. It happens that all of the procedures introduced by his transformation were continuations, but they were not labeled as an idea. And so it didn't, in fact, even Van Wijngarden, I don't think, ever used the concept of continuations in later work. I'll just let you read the second quote. Maybe I'll make that easier. So, semantics is never far from methodology. The next person I'd like to mention is someone who I have never actually met, A.W. Mazurkiewicz. He wrote a paper, I guess the earliest working paper was circulated in 1969. And he was describing an automaton in which the states were composed of labels and dynamic states. And he then defined what he called a tail function, which would take one of these states and map it into the final result of the automaton. If the automaton was in that state. And that's quite easy to define recursively, and it is, of course, being the rest of the computation from the state, it's a continuation. The trouble is that it's in such a limited context that you really can't see what continuations, it's just a tip of the iceberg. But it was a clear tip of the iceberg, and he at least gave these things a particular name and pointed to them and said, this is a concept. And so he had some influence. But at least from my experience of the history, the next thing to mention is Lockwood Morris. Morris gave a talk at Queen Mary at Peter's invitation in 1970. And he showed a number of definitions of a call by value language with, I think, assignment. By means of interpreters, which were either written in the same language or in Lisp, I forget which. And the last of those interpreters used continuations. And in fact, he called those continuations dumps, setting up a definite linkage with Peter's work. But in his case, those dumps were functions. They were the functions that would be represented by Meining's dumps. And the question is where he got the idea. In email, he said, I think my main inspiration were functions in the Lisp programming manual. For example, search. You give search an extra argument, which is a function which carries out the rest of the computation in the case where the search fails. And similarly, he did a definition of snowball in which the meaning of each pattern match mechanism was a function that took two continuations arguments, one to be evaluated if the search succeeds, the other to be evaluated if it fails. Incidentally, there's an exhibit of some original papers which include the notes that Lockwood passed out at that colloquium. I should mention that I had the good fortune to attend the colloquium, which was my first direct thing. So the result was that I understood continuations at a very early date without having any claim to contributed to them. But what I did do was to take a trip to Edinburgh a month later, and I visited Rob Burstall, and Burstall was in the midst of a conversation with Chris Wadsworth, who was at that time a graduate student of Strachey's in Oxford. And Burstall asked me, this was in November of 1970, what was happening at Queen Mary, and I said not too much, but we heard a really interesting talk by Lockwood Morris, and I started to explain what Lockwood had said, and Wadsworth looked very amazed and said, that's what I'm doing. And in fact, he was, in a formal sense, doing exactly the same thing, except that instead of writing an interpreter to define the language, he was using Scott's new denotational semantics, or as it was then called, the lattice theory of computation. This is his reply when I asked him for email. Actually, this is an email he sent to Amr Sabri that Sabri forwarded to me, and the others are email quotes directly from Wadsworth. And the central point here is that what gave him the spark he needed was the paper by Mazurkiewicz. Further quotes from Wadsworth. I think this business about getting the right word is really something to take seriously. And the next quote is something I particularly enjoyed, because of course Wadsworth was doing this work in November of 1970, and the first written accounts of it appeared informally. And what's the date on that? Do you remember? The paper by Strachey? Hmm? No, the Strachey one.
Just straight. That's, I think it's something. 71. 72? Is that Josh?
I might believe 72. But,
Carry on, Joe.
okay. I'm almost certain, because when Wadsworth got his degree, he came to Syracuse and worked with me.
Well, straight
Yeah.
and Wadsworth is 74.
Yeah, I know that. That's a publication. Or not, no, it's a PRG report. And I know there was an earlier one at Area, but I haven't seen this one before. I don't think. Is there a date on it?
No, I don't think there is actually.
It's got one comment that's nice.
Can you find it? You might want to wave that and point it out. That's the less interesting.
I'll pass it back. Eventually, Strachey and Wadsworth wrote a joint report on this, and there appear to be a few things circulated earlier. It's my impression, I will admit I use Wadsworth a lot better than I use Strachey, that it was Wadsworth's idea, but the actual writing of those reports is all Strachey's. Well, this was the year that Wadsworth finished his thesis. In his thesis, he did the definitive explanation of Scott's D infinity, in the sense of saying what was different about it than all other models of lambda calculus. And he also invented graph reduction, and then continuations. And that's too much for a person to come up with in 1 year and publish promptly, quite aside from the remarks here. I think it's actually the most fertile short period of ideas that anybody in computer science has ever done.
John, Peter Moss is here. Does Peter know the date?
My impression is that there was something floating around in 72, and I based a paper of my own on Algol 60 using continuations in 73 as a PRG report.
I'm sorry.
In 73, I had a paper that was actually using continuations to describe Algol 60, and that was in 73. That was a PRG report.
Mm-hmm.
So I think 72 is most likely date.
That sounds plausible. What's your opinion as to how much of it was Wadsworth's discovery?
It's a good question. I go along with you on that. I think that it really was Wadsworth's original ideas, and Strachey was the disseminator more than the originator.
Well, the writing certainly sounds like Strachey. I don't think Chris would have written that way. And then there was Jim Morris. Let's see if I have dates here. Yes, in 1971, he discovered the CPS transformation and applied it originally to a lambda calculus-based language in order to probably replace call by value by call by name. And then when he decided to publish this, he thought he would get a wider readership if he applied it to a real programming language, and he applied it to Algol, and he sent it to the communications of the ACM, and through the auspices of some referee that I do not know the name of, and neither does Jim, the paper was rejected because it had all been done by Van Wijngarden. And Jim, in fact, managed to salvage the fact that you could apply it to a more general language than Algol, in which the procedures returned complex values, and it would eliminate them. And so what it ended up with is a letter to the editor called a bonus from Van Wijngarden's device. And I think I'm not violating confidence to say that Jim was not happy about this. Particularly since if he had left it clothed in the opacity of the lambda calculus, it would have been accepted. The other curiosity, of course, is it was the title of that paper that clinched Van Wijngarden's claim to having discovered continuations. Then there was Mike Fischer. Fischer, who was more in the what we used to call the schematology community and complexity and so forth. Maybe I should just say who was not a Euro theorist. Extended the call by value lambda calculus with conditional expressions and non-interpreted constants and primitive functions. And he described the transformation of this functional language in a continuation passing style. And his purpose was to show that you could transform an arbitrary program by the CPS transformation into a form that can be implemented by a stack. Admittedly, a stack that never pops, but still a stack. What's notable is that Fischer actually proved relationships between the related meanings in these things to show that the transformation preserved meaning in an appropriate and necessarily complicated sense. And this was, I think, the first proof about the semantics of continuation. It certainly predates the proofs using denotational semantics. He gave that in a paper at what was called Proving Assertions About Programs conference in Las Cruces in 1972. And I distinctly remember at the break, Jim Morris. Oh, I completely forgot to mention. The two Morrises are second cousins. This is the only case, I'm sure, in which major scientific discovery has been made independently by relatives. So, during the coffee break, I had the first coffee break in this conference when we had just all been leafing through the proceedings. Jim Morris walked up to me and he said, "Guess who's discovered continuations now?" And I saw him tiptoe over to Fischer and say, "Mike, I have news for you." I think the last person I will mention is Kamil Abdali, who used continuations in his thesis at the University of Wisconsin. And what he was doing was essentially defining Algol in terms of pure call by name lambda calculus. He gave a paper at the Computer Science Conference in Columbus, Ohio, describing the idea rather briefly. He then submitted a paper to the first POPL, and it was rejected. And it was rejected because I was on the program committee and I said it should be rejected. Abdali has permitted me to mention the fact the paper was rejected, and I think I should say that because of all of my duties as a referee, this is the one I think I'm least happy about. I felt it should be rejected because there was no discussion of procedures, and that's what you have to get right in order to have a definition of Algol. And of course, what I didn't know was that he had done procedures and he had done them right, and that he had just cut that out because he wanted to meet page limits. And his advisor didn't have the sense to warn him that that's the stuff you have to let people know about. But in fact, he got it right, and later I think people came to understand and appreciate it. It was Jim Morris who eventually pointed out to me that Abdali had gotten the definition, which in fact, in many respects, pre-shadows the work I did years later on function category definitions. The interesting thing about this is that Abdali's thesis advisor was George Petrick, I think was the name. I'm sorry, I don't have it in front of me in my notes. And Petrick had been a student of J. Barclay Rosser, of Church Rosser fame. And it had been Rosser who had been the impetus behind the thesis subject, because Rosser was unhappy with your definition of Algol using lambda calculus. He felt that by extent, I'm speaking to Peter Landin, he felt that by moving to a call by value language and adding things like assignment and so forth, that you would make it difficult to use the correspondence for deriving properties of programs, and because of that, he wanted Abdali to translate the constructs into the pure lambda calculus, meaning call by name. Well, by that time, continuations were widely enough understood that a well-educated person in the field could not really discover them. Not that much more has been learned about them. We now have a conference every couple of years in continuations. There have been some fascinating things. I think two that are worth mentioning, though I can't give citations. One is the connection with the Curry-Howard isomorphism, which allows you to talk about classical logic instead of just intuitionistic logic. And the other is a paper I heard in January. There was a satellite conference on continuations, workshop on continuations for Popple. And they had a guest speaker whose name I regret escapes me, but he discussed the application of continuations in natural language semantics. And it was absolutely fascinating, but essentially they are just a wonderful tool for explaining things like pronoun binding and such matters. And I think that's all I have to say. We have a few minutes left for questions. I would be happy to entertain questions on other topics than continuations, as well as on continuations. Josh?
I'll just make a comment that the last two things you mentioned.
Could you speak up a bit?
Sorry, the last two things you mentioned, the connection with classical logic, you can look to Griffin for that.
I'm sorry, I can't hear you.
Oh.
And are we recording this?
We're trying to. The questioners, I don't think.
Okay. So to just supply names for the last two things that John mentioned, the connection with classical logic is Griffin. I don't remember the first name. Tim. Okay, and the national language stuff is Barker.
Barker. Okay. University of Michigan? Okay, I don't know.
John, so after, can you give a one sentence definition or two sentence definition of continuation? I ask because I'm actually confused.
Oh. So you don't just want a definition, you want a definition that will eliminate your confusion?
Yes.
I better say no. But if I had to say in one sentence to describe what it is, it's a function mapping some current state or value in a computation into the final result.
Is that a representation? Sorry.
No, I don't think so because of extensionality. If that function is different, then there is some state that you could be in that would lead to a different result. Yeah.
I vaguely remember somebody in Birmingham, I don't know the name, it's Hugo, is describing all the continuations in terms of category theory.
IoT.
Okay, I'd like to ask a different question.
Okay.
And this
I'm
is.
sorry, I should make some reply to that. I'm not familiar enough with Hayo's work to comment on it in any detail. But obviously, there is a huge amount of work using continuations, including work in category theory, that I haven't been able to touch on in this presentation. Peter? Okay.
So my question is, continuations considered harmful. In a language that you designed, I think you allowed the assignment of various things, including procedures, to variables.
Mm-hmm.
And I wonder if the generality, the power of continuations, didn't actually lead people into what I regard as mistakes in programming language design.
I have two instincts, one of which is to say yes and the other is to say no. And I think the real situation is this. No, they are not mistakes in language design. I'm not sure how you would define exactly what a mistake in language design is. One thing is something that encourages people to write bad programs. There is a class of programs that cannot be written without first-class continuations. I'm not talking about what the programs do, but how the programs are structured. For instance, if you want to take some interesting subroutine like a parser and backtrack it, you have to have first-class continuations to isolate that parser. Okay? And that means that there is a way of programming that is impossible without continuations. And if you want a language to support it, you have to understand them. And if you don't understand them, if you misunderstand them, you can botch it. On the other hand, I'm certainly not saying that a programming language has to provide first-class continuations in order to be an important programming language, because there are certainly problems where of implementation where it is difficult to avoid producing poorer implementations of code that makes no reliance on continuations. Okay, I think that would be a big problem. Yeah.
So one of the main habits in denotational semantics is to provide a standard description of a language by immediately going to continuations and using it as a way to represent sequencing, even in the absence of fancy things like go-tos.
Mm-hmm.
On the other hand, continuations are rather sequential in nature, in that it's really quite difficult to combine that with specifying something like interleaving in the same description. Rather have to go to something like resumptions, I think, to get the effect of somehow allowing continuations to be interleaved in some way. I wondered if you had any comments about the appropriateness of using continuations as a general hammer to hit all the nails in the programming language world.
I'm in complete agreement with what you said. And I think if I said it, I might say it even more strongly. I'm particularly aware of this because I'm currently involved in developing something called separation logic. And there are two directions we want to extend separation logic into. One is into dealing with shared variable concurrency, and the other is in permitting first-class continuations. And we can't do them both at the same time or compatibly. And that is a real pain.
Okay, well, can I thank John